Hey class, Adam Ward here. I want to talk with you today about measuring photosynthesis and respiration in aquatic systems. What we'll talk about today goes along with lecture 24 in your Chopra textbook. So when we start to work on photosynthesis, we run into one challenge, which is that photosynthesis is directly proportional to irradiance or available light, the intensity of sunlight reaching the Earth, for which we use a capital I. So prior to this, everything that we've done in class has had a rate that's been constant, just a first order rate coefficient, a k. We were happy to deal with that. But now we've got a rate that's actually going to start to vary through time. And so what I want to do in this lecture is take a look at how that variability can be expressed mathematically, and then think about ways that we can estimate photosynthesis and respiration in our systems. So if we think about what a typical day looks like, it might plot something like this, where the y-axis would be photosynthetic activity or solar irradiance. So if this is a typical sunny day, the sun rises and sets, and Chopra uses TR and TS to denote time of rise and time of set. Just to get ourselves oriented, the peak of solar intensity is called solar noon. For the most part, we're working on cycles that are one day. You don't have to be, and so if you want to make adjustments, Chopra helps you with that by using this capital T sub P. But for the most part, we'll be working on a frequency of one day. And then a couple of notes. The fraction of the day when you actually have light, so the fraction of that TP value when you're in light, is denoted with this lowercase f. It's the time elapsed from rise to set on top divided by the total time period on the bottom. So if you have 12 hours of light, the fraction in light in a day would be 0.5. Finally, the peak of that solar intensity we'll denote with a P max or an I max, giving us sort of where is the apex of that half sinusoid shape. And again, that's occurring at solar noon. Okay, so qualitatively, we've got a lot of new descriptors, but basically the sun rises, the sun sets, and we're going to think about when that peaks and what fraction of day it's light out. Now with that information, we can start to think about different ways to express photosynthesis through time. I'll show you three options here. First option being what I call the fully time variable option. So that's actually trying to represent photosynthesis as I've sketched it out in orange. If you want to do that, what you're actually doing is representing the sunlight as a half of a sinusoid. And so you can see that dependency here is going to be on that maximum amplitude or that maximum value, your fraction of time in daylight, lowercase f, and how far you are past the time of sunrise. And importantly, that's only going to apply between sunrise and sunset. So that equation actually defines a sine wave, and what you need to then do is say, well, okay, it's a full sine wave, but I only want the part from rise to set. At all other times, I'm going to use zeros. So this would be a fully time variable representation of photosynthesis. One way that people tend to make this simpler excuse me, is to use an average daylight rate. And so the idea of an average daylight rate is maybe I don't really care so much about the dynamic of the rising and falling, but I do know that the sun is functionally turning on and off through the day. So you make this a binary problem. Is there sun or is there not? Again, if you're not between rise and set, you're using a value of 0. And if you are between sunrise and sunset, you're calculating photosynthesis as a constant rate, that P max multiplied by 2 times pi. So you end up with that P that I've drawn in blue. And then the final simplification would be to pick an average daily rate, in which you say, look, I'm not going to treat photosynthesis as time variable whatsoever. Sun turns on, sun turns off. What's the average over the course of a day? And so in that case, you're not putting any zeros at night. Instead, you're taking all of that area under the curve and smearing it out equally over your time period. And so you can calculate that as the maximum photosynthesis rate, P max, multiplied by 2 times that fraction in daylight over pi. So 3 different ways to do this. A question that I'll leave to you all to think about and that we can discuss in lecture a bit. Why might you select different formulations? Why not always use the time variable? Why not always use an average daily rate? In what situations would different simplifications or complications of this process be more beneficial to us as water quality modelers? So you all can think about that a bit. Now, we've got some ability to represent photosynthesis, but what we still haven't done is actually figure out how do we calculate the darn thing. Right? In all of these cases, we need to know something about P or P max, and so what I want to talk through next are 3 different ways that we can do this. The first way is called the light bottle, dark bottle method. This is very classically done in stream ecology, aquatic biogeochemistry. It's fairly similar to the way we would do a BOD test. We're going to use oxygen levels inside of bottles as a proxy to understand what's actually happening there. And so what you can see in the photograph here are a series of paired bottles, clear, so light can penetrate them, and you will get both photosynthesis and respiration. And then dark bottles, which exclude the sunlight, and so in theory you're only getting respiration inside of that bottle. Now our setup here is fairly simple. We measure the oxygen concentrations initially, and so I've denoted those with the subscript I. Light bottles also have an L. We measure the oxygen level when we pull this thing back out after some time t, and the net photosynthesis rate can be calculated as the difference in those 2 values divided by time to make it a rate. And the idea here is that the net change is going to reflect the gross photosynthesis in the bottle, PB, minus the respiration that occurred inside of that bottle, R community. Now, you've also got a dark bottle that lets you make an estimate of that community respiration. And so again, you're using the change in oxygen through time to estimate community level respiration. That's all the different activities that are going on inside the bottle. So that's both the respiration process and the decomposition of organic matter that gave us BOD. So the final thing that we often will try to do then is separate out how much of this was respiration, R, versus how much of this came from biological oxygen demand. And so in order to do that, you need to have an estimate of KD, that decomposition rate, and you would need to know the BOD that you started with inside of your light bottle. So measuring oxygen in a light bottle before and after, dark bottle before and after, and having some estimate of BOD in your water is an easy way to get values for both P and R. The second method that Chopra proposes is called the biomass method. I won't show you the equations here, but we will talk through it. In this process, you're estimating photosynthesis and respiration rates as a function of biomass growth. Now, in order to do this, you need to know several things. You would need to know what is the optimal growth rate for your species. So lacking any limitation, how fast would that algae grow, for example? You need to know water temperature, so we'll do an Arrhenius equation type correction. You need to know the concentration of biomass itself, and you need to know something about light attenuation. The idea that light that hits the surface of the sun is the surface of the water is not the same throughout the column, but actually decays exponentially as you move down in depth. The equations for this are presented in Chopra 24.2.2, and for purposes of time here, we'll leave it to you to work through those if you choose to. The final method is called the delta method. This is presented in Chopra 24.2.3. And this method relies on making observations of DO and deficit in the stream itself. And so I'd say largely a graphical method, and I want to just walk you through this. So the idea would be that we're going to assume respiration is constant through the day. We're going to treat photosynthesis as a function of light intensity, which we could readily measure the patterns of. And so we would get observations from a system that look like this. We'd have photosynthesis and respiration theoretically happening as I've drawn above. We would have measurements of oxygen through time and saturated levels. And the idea here would be then, if you know OSAT and you know DO, you can calculate your deficit. And then there are two key parameters that you need to pull out of here. One is this parameter phi, and that's the offset between solar noon and peak oxygen levels in the stream. And so if you know when and where you were on Earth, you can basically calculate what time that solar noon should occur. You can use your data to estimate the peak oxygen level and get that phi. And then the second parameter you need is the delta, and that's basically the range of deficit. So the highest value of deficit minus the lowest value of deficit you had through the day. Chopra goes through the equations for this. I'll show you the shortcut, which is graphical. There are two plots in lecture 24 that you'll need. The first is a plot of phi against Ka, and it's got several lines on it. As you move left to right, those are in order of increasing values of F, that fraction of day in sunlight. And the idea is that from your field data, you would calculate, and second plot, looks like this. Delta over P on the y-axis and that Ka on the x-axis. Again, different values for F. The idea is that you have field data, and from your field data, you can calculate that phi. You also know the fraction of day in sunlight. So using the first graph, you bounce up to the correct value for F and then over to the y-axis to get a Ka value. On the second plot, you start with that Ka value, you bounce up to the correct fraction of day in sunlight, and over to the delta divided by P value. And when you do this, you basically end up with some number that is representative of delta over P. That's the number that you're reading off of the y-axis in the second plot. Great, we can measure delta from our field data. So we've got one equation, one unknown, and we can solve for photosynthesis as whatever number we read off the y-axis divided by the delta that came from our field data. So at this point, you should have some sense of how we can represent time variable processes, particularly time variable processes that are following this half sinusoid, like our sunlight, and rates that are directly tied to it. And you should be able to describe something about the three methods that we have to measure photosynthesis and respiration. That's light bottle, dark bottle, biomass, and delta method. In the next video, I will work through a light bottle, dark bottle example, and in one of the Chopra homework problems, he walks you through the delta method. Thank you very much for your attention, and I will see you in class.